Deep in the fabric of the cosmos, something extraordinary is happening. Ripples in the very structure of space and time itself, traveling across the universe at the speed of light. These are gravitational waves, the echoes of the most violent and extreme events imaginable. Black holes colliding, neutron stars tearing each other apart, even the birth cries of the universe in its earliest moments. And today, we're diving into the most astonishing, mind-bending examples of these cosmic tremors, phenomena so powerful they warp reality itself. Imagine the universe as a vast, silent ocean. Now picture two massive objects like black holes, each weighing billions of times more than our sun, spiraling toward each other at nearly the speed of light. When they collide, they release energy equivalent to trillions of atomic bombs exploding at once. That energy doesn't just vanish, it shakes the fabric of space-time, sending gravitational waves rippling outward, stretching and squeezing everything in their path. And somehow, here on Earth, we've built machines sensitive enough to detect these whispers from the edge of reality. But why should we care about these invisible ripples? Because they're like cosmic messages, carrying secrets about the most extreme places in existence, places where gravity is so strong it bends light into knots, where time itself slows to a crawl. Gravitational waves let us hear the universe in a way telescopes never could, revealing hidden chapters of the cosmic story. And some of these waves are so extreme, so bizarre, they challenge everything we thought we knew about physics. Over the next few minutes, we'll uncover 30 of the most jaw-dropping gravitational wave discoveries, from dead stars dancing in perfect harmony to supermassive black holes hurling each other across galaxies. Buckle up, because the universe is about to show you just how strange and magnificent it really is. The universe had been keeping one of its greatest secrets for 100 years, until September 14, 2015. That's when scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, caught something extraordinary: the faintest ripple in space-time, a signal so tiny it stretched their detectors by less than 1,000th the width of a proton. Yet that whisper, labeled GW1-509414, was anything but small. It was the echo of two black holes, each about 30 times the mass of our sun, spiraling toward each 1.3 billion light-years away. When they collided, they merged into a single, even more massive black hole, and in that final, violent moment, they converted 3 times the mass of our sun into pure energy, shaking the fabric of space-time itself. This wasn't just a discovery, it was a revolution. Einstein predicted gravitational waves in his theory of general relativity back in 1916, but even he doubted we'd ever detect them. The distortions were simply too minuscule, lost in the noise of a restless universe. Yet LIGO twin observatories, one in Louisiana, the other in Washington state, acted like cosmic microphones, picking up frequencies lower than any sound we could hear. The signal matched Einstein's equations perfectly, proving that space-time isn't just a static stage for the universe. It's a dynamic, flexible fabric that bends, warps, and even shudders under the weight of cosmic collisions. What made this detection so groundbreaking? For the first time, we weren't just seeing the universe, we were listening to it. Telescopes show us light, but gravitational waves carry the soundtrack of the cosmos, revealing events no telescope could ever spot. Those two black holes left no glowing remnants, no burst of radiation, just a ripple in the dark. Without LIGO, we'd never have known they existed. This opened an entirely new way to explore the universe, like switching from silent films to surround sound. And the best part, we're just getting started. Every new detection peels back another layer of the universe's most extreme phenomena, rewriting textbooks one cosmic tremor at a time. Picture tossing a pebble into a still pond. Those gentle, expanding rings are exactly how gravitational waves move through the cosmos, except instead of water, they're rippling through the very fabric of spacetime itself. When massive objects like black holes or neutron stars accelerate, whether they're orbiting, merging, or even exploding, they don't just move through space, they twist and stretch the invisible grid of reality around them. These distortions surge outward in waves, carrying energy, momentum, and crucial details about the events that birthed them. What's mind-blowing is how fast these waves travel, at the speed of light, crossing the entire universe without slowing down. Unlike light, which can be blocked by dust or swallowed by black holes, gravitational waves slip through everything untouched. A collision of black holes in a distant galaxy might leave no visible trace, but its gravitational ripples pass right through planets, stars, even you, stretching your body by an infinitesimal amount as they go. And here's where it gets even wilder. These waves encode the stories of their origins. The shape of the ripple tells us what kind of cosmic catastrophe created it, whether it was two neutron stars circling each other in a death spiral or a supermassive black hole shredding a star apart. The frequency of the waves reveals how massive the objects were, while changes in amplitude hint at their speed and trajectory. It's like listening to a cosmic fingerprint, each one unique. Think of spacetime as a vast, silent auditorium. Until recently, we were stuck watching the universe through a keyhole limited to what light could show us. But gravitational waves, they're the symphony of the cosmos, vibrating the walls of reality itself. And now, for the first time in history, we've tuned in. Scientists were still reeling from their first gravitational wave discoveries when, in May 2019, the universe delivered an event so violent it rewrote the record books. This time, the signal wasn't a faint whisper. It was a cosmic shout. LIGO and its European counterpart Virgo detected a gravitational wave so powerful, it stemmed from the collision of two black holes with a combined mass 66 times greater than our Sun. When these monstrous objects finally merged, they unleashed energy equivalent to 8 entire suns vaporized into pure ripples across spacetime, making it the loudest gravitational wave ever recorded. But what made this event, labeled GW190514, truly extraordinary wasn't just its sheer volume, it was the puzzle it left behind. The larger of the two black holes weighed in at a staggering 85 solar masses, which defied everything we thought we knew about how black holes form. Stars that massive should destroy themselves in pair instability supernova, leaving no black hole behind. Yet here was undeniable proof of a black hole existing in this forbidden mass range, a cosmic glitch that sent theorists scrambling back to their chalkboards. The collision itself played out like a slow-motion cosmic ballet. Over billions of years, these black holes had been circling each other in what astronomers call an in-spiral, a death spiral where they lose energy through gravitational waves, drawing inevitably closer. When they finally merged 7 billion light-years away, the resulting black hole wasn't just massive. It was spinning at nearly half the speed of light, warping space-time around it like a celestial whirlpool. The aftershocks from this event rang across the universe like a gong, stretching and compressing spacetime so dramatically that even after traveling 7 billion years, the wave still deformed LIGO detectors by 1,000th the width of a proton. For astronomers, this detection was like finding a Tyrannosaurus Rex in your backyard. It proved the existence of black holes in a mass range we didn't think possible. Some now speculate these could be second-generation black holes, formed from earlier mergers in dense star clusters. Others wonder if we're seeing evidence of primordial black holes forged in the chaos of the Big Bang itself. One thing's certain, the universe is far stranger and far louder than we ever imagined. And with each new gravitational wave detection, we're not just hearing the cosmos, we're decoding its deepest, most violent secrets. For nearly a century, scientists had dreamed of catching two neutron stars in the act of colliding, and in August 2017, the universe delivered. This wasn't just another gravitational wave detection. It was the cosmic equivalent of a fireworks finale, an event so dazzling it lit up the sky in gamma rays, X-rays, ultraviolet, and even visible light. The collision, officially named GW1-70817, marked the dawn of multi-messenger astronomy, where we don't just see or hear the cosmos but do both simultaneously. The drama began when LIGO and Virgo picked up a ripple lasting a record 100 seconds, far longer than the abrupt chirps of black hole mergers. This was the signature of two ultra-dense neutron stars, each just 12 miles wide but weighing more than our Sun, locked in a lethal spiral. As they circled each other thousands of times per second, their immense gravity warped spacetime like a spinning top wobbling on a table. Then, in a cataclysmic finale, they smashed together with such force that the resulting shockwave forged entire planets' worth of heavy elements, including gold and platinum, in mere seconds. What made this discovery revolutionary wasn't just the gravitational waves. For the first time, telescopes worldwide caught the afterglow, revealing a kilonova, an explosion 1,000 times brighter than a typical nova. The Hubble Space Telescope even spotted the telltale infrared glow of freshly minted gold and platinum, solving a cosmic mystery where half the universe's heavy elements originate. Before this, we assumed supernova forged them, but the kilonova's spectrum showed neutron star collisions are the universe's ultimate goldsmiths. The data also settled a heated debate about gamma-ray bursts. The collision produced a short gamma-ray burst just 1.7 seconds after merging, proving these intense flashes arise from neutron star mergers. Even more astonishing, the ejected material raced outward at nearly 1/3 the speed of light, glowing brighter than 1,000,000 suns for days. But perhaps the most profound revelation was how spacetime behaved during the event. The gravitational waves arrived at Earth 2 seconds before the gamma rays, not because they traveled faster, but because they slipped through the universe unimpeded, while light had to fight through debris. This tiny delay confirmed Einstein's prediction that gravitational waves move at light speed, with precision down to 1 part in a quadrillion. Overnight, GW1-70817 became the most studied astrophysical event in history, involving 70 observatories and over 4,000 scientists. It proved that when neutron stars collide, they don't just shake spacetime, they paint it with the very elements that make up our wedding rings, smartphones, and even the iron in our blood. Suddenly, the universe felt less like a void and more like a vast, interconnected forge, where the most violent events create the building blocks of life itself. The universe loves extremes, but nothing prepares you for the sheer scale of supermassive black hole duos, cosmic behemoths weighing billions of times our Sun's mass, locked in orbital dances that last millions of years. Unlike the stellar black holes we've detected so far, these titans don't just create gravitational waves, they generate space-time tsunamis, ripples so vast they could stretch across entire galaxies. And while we haven't heard them yet, future observatories like the Laser Interferometer Space Antenna, or LISA, are being designed to tune into THESE, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter. Picture two supermassive black holes, each anchored at the heart of a merging galaxy, circling each other like gravitational sumo wrestlers. Their orbits are so wide, one lap could take decades, but the energy they shed as gravitational waves would dwarf anything LIGO has detected. A single merger of these giants could unleash waves with frequencies 1,000,000 times lower than those from stellar collisions, vibrating spacetime itself like the deepest notes of a cosmic cello. Why haven't we spotted them yet? Earth-based detectors like LIGO are built to catch high-frequency waves from smaller black holes, the cosmic chirps lasting seconds. But supermassive duos hum at frequencies too low for ground instruments, their waves spanning light years in wavelength. That's where LISA comes in, a trio of spacecraft set to launch in the 2030s, floating in perfect formation millions of miles apart. They'll act as the universe's most sensitive tuning fork, detecting waves by measuring microscopic shifts in distance between the satellites, shifts smaller than the width of a single atom. The implications are staggering. Supermassive black hole mergers could reveal how galaxies evolve, as these collisions likely shape the structure of the cosmos itself. Some theorists even suggest these waves might carry echoes from the Big Bang, hidden in the lowest frequencies like whispers trapped in a canyon. Every second we wait feels like holding our breath, because when Lisa finally listens, it won't just hear the universe's loudest crashes. It'll decode the bassline of existence itself. That unmistakable sound, like a bird's chirp sweeping upward in pitch, isn't just a simulation. It's the actual voice of two black holes singing their final duet before colliding, captured by LIGO instruments and translated into something human ears can hear. Scientists call this the chirp signal, and it's one of the most profound sounds in the universe. But how do you turn a ripple in spacetime into audio? The secret lies in the way black holes behave as they spiral toward catastrophe. As the black holes orbit each other, they lose energy through gravitational waves, forcing them to spiral faster and faster. This creates a wave frequency that rises exponentially. Imagine a skater pulling in their arms to spin quicker, but on a cosmic scale. LIGO detects these waves as a series of squiggles in its data, with each oscillation corresponding to a stretching and squeezing of spacetime. To convert this into sound, researchers simply speed up the signal. The original waves might span minutes or even hours, but compressing them into seconds shifts their frequency into the range of human hearing. What emerges is that iconic upward sweep, a direct sonification of the black hole's fatal dance, crescendoing as they merge. But here's what's haunting: that chirp isn't happening now. It's a delayed broadcast from an event that occurred billions of years ago, when Earth was still a lifeless rock. The waves traveled through the void at light speed, untouched by time or distance, until they finally reached our detectors. Every chirp is a cosmic time capsule, carrying vibrations from an era before multicellular life existed. Why does this matter? Because the chirp's shape tells a story. The steepness of its rise reveals the black hole's masses, while the way it cuts off abruptly after the merger hints at the new black hole's stability. Some chirps even ring down, faintly like a bell struck once but reverberating, as the merged black hole settles into its final form. It's as if the universe left us a voicemail, and scientists are just learning to decode its meaning. And sometimes that voicemail holds surprises. In 2019, LIGO caught a chirp that didn't match any known black hole collision. WGW1 90426. The signal peaked and vanished in just 10 milliseconds, so fast it might have been two ultra-dense objects like neutron stars smashing together at unthinkable speeds. Or perhaps something even stranger, like a black hole tearing apart a neutron star in a single, violent gulp. Each chirp is a fingerprint unique to the event that birthed it. And with every new detection, we're tuning into a cosmic orchestra playing the soundtrack of the universe's most extreme moments. Before black holes, before stars, before atoms even existed, the universe was a seething ocean of energy, and buried in that chaos may lie the oldest gravitational waves of all. These aren't the ripples from colliding black holes or neutron stars. They're echoes of the Big Bang itself, vibrations left over from the moment spacetime exploded into existence. Scientists call them primordial gravitational waves, and if we could detect them, they'd be our closest thing to a time machine, carrying whispers from the universe's very first trillionth of a second. The theory goes like this: in the instant after the Big Bang, the universe didn't just expand, it inflated, ballooning from smaller than an atom to the size of a grapefruit in less than a billionth of a second. This runaway expansion, known as cosmic inflation, would have stretched the fabric of spacetime so violently that it generated gravitational waves powerful enough to persist for 13.8 billion years. Unlike the sharp chirps LIGO detects, these waves would be a low, steady hum, stretched by the expansion of the universe into wavelengths longer than our entire galaxy. Why haven't we found them yet? The signal would be incredibly faint, buried in the cosmic microwave background, the afterglow of the Big Bang itself. But there's a telltale signature. These waves would have subtly polarized the ancient light, twisting it in a distinctive swirling pattern called B-modes. In 2014, the BICEP 2 telescope team thought they'd spotted this smoking gun in data from Antarctica, but it turned out to be cosmic dust mimicking the signal. The hunt continues with next-generation telescopes like the Simon Array and CMB-S4, designed to filter out false clues. What makes this so revolutionary? Detecting primordial waves would confirm cosmic inflation, revealing what powered the universe's exponential growth. Some theories suggest inflation was driven by a mysterious field called the inflaton, a cosmic engine that briefly made gravity repulsive instead of attractive. Others speculate these waves could carry imprints from even earlier, hinting at a multiverse or a cyclical cosmos where big bangs happen over and over. But perhaps the most mind-bending possibility is that these waves might let us peer beyond the Big Bang. Normally, the universe's first moments are hidden by a wall of plasma so dense not even light could escape. Gravitational waves, though, slip right through. If we catch them, we might finally answer the ultimate question: how did everything, space, time, matter come from nothing? It's the universe's oldest secret, written in vibrations quieter than a heartbeat across 13 billion years, and we're listening. Most gravitational waves we've detected are like cosmic fireworks, brief, explosive bursts from black holes or neutron stars colliding. But hidden in the cosmic static might be a subtler, more persistent signal: continuous gravitational waves, a faint, unending hum from objects spinning relentlessly across the universe. Imagine a neutron star, a city-sized remnant of a supernova, so dense a teaspoon of it would weigh 1 billion tons, spinning hundreds of times per second. If it's even slightly asymmetrical, say, with a mountain just millimeters tall on its surface, its rotation would send out gravitational waves like a lighthouse beam, steady and unchanging for millions of years. Why haven't we caught one yet? These waves are whispers in a hurricane. Compared to the violent chirps of black hole mergers, continuous waves are millions of times weaker, their signal buried under seismic rumbles, passing trucks, even waves crashing on distant shores. Detecting them is like trying to hear a single violin playing softly in a stadium packed with roaring fans, but the payoff would be extraordinary. A continuous wave would act as a cosmic tuning fork, letting scientists probe neutron stars with impossible precision. The wave's frequency could reveal the star's spin rate down to a fraction of a millisecond, while tiny shifts might hint at quakes reshaping its surface. Most tantalizing, these waves could expose the true nature of ultra-dense matter. Neutron stars are so compressed, their cores might contain exotic states-free quarks, superconducting fluids, even stranger materials that defy the laws of earthly physics. A continuous wave's stability could serve as a laboratory for testing these theories, indirectly mapping the star's interior through its gravitational hum. The hunt is already underway. Observatories like LIGO and Virgo are running specialized searches, sifting through years of data for telltale patterns. Some teams even use volunteer-powered projects where home computers scan for signals in their downtime. And there's hope. In 2023, a candidate signal, slightly louder than the noise, sparked excitement, though confirmation is still pending. What keeps scientists searching is the possibility of stumbling onto something even weirder. A continuous wave might not come from a neutron star at all, but from primordial black holes formed in the Big Bang, or cosmic strings, hypothetical flaws in spacetime itself. Until we find one, the universe's quietest song remains just out of earshot, a melody spun from the fabric of reality, waiting to be heard. Somewhere in the constellation Sagittarius, a cosmic record breaker spins faster than your kitchen blender, 516 times every second. This is PSR J1-748-2446 AD, the fastest known pulsar in the universe, flinging beams of radiation across space like a lighthouse gone berserk. But what's truly astonishing isn't just its speed. It's the gravitational waves this stellar speedster might be generating, ripples that could unlock secrets about matter pushed to its absolute limits. Pulsars are neutron stars, the collapsed cores of dead stars packing more mass than our sun into a sphere barely the size of a city. As they spin, their immense gravity and magnetic fields whip radiation beams around like cosmic searchlights. But PSR J1748 isn't just any pulsar. Its breakneck spin means its equator is moving at nearly 1/4 the speed of light, flattening it slightly like a pizza dough tossed too fast. And that tiny deformity, perhaps just a few millimeters taller at the equator than the poles, could be warping spacetime itself, sending out a steady hum of gravitational waves with every rotation. Here's why that matters. Those waves act like an X-ray for the pulsar's soul. By measuring their frequency and strength, scientists could map the star's shape with unprecedented precision, revealing whether its crust is smooth or fractured, or if its core contains exotic states of matter like free-floating quarks. The waves might even hint at mountains on the surface, not real mountains, but microscopic bumps mere millimeters high, yet dense enough to distort spacetime as the star spins. But detecting these waves is like listening for a single instrument in a symphony. Pulsar waves are millions of times weaker than those from black hole collisions, drowned out by cosmic noise. Current observatories like LIGO aren't sensitive enough to catch them, but next-gen detectors like the Einstein telescope or the Cosmic Explorer could finally tune in. If they do, it'll open a new window into neutron star seismology, letting us study quakes and shifts in these ultra-dense objects through their gravitational fingerprints. What's at stake? PSR J1748's waves might solve a cosmic mystery: how neutron stars can spin so fast without tearing apart. Some theories suggest their interiors are superfluid, flowing with zero friction, while others propose bizarre, hyperion particles that only exist under such extreme pressure. Every ripple carries clues, turning this pulsar into a natural laboratory for physics we can't replicate on Earth, and the implications stretch even further. If we confirm continuous waves from pulsars, we might finally understand how some of them accelerate to such insane speeds in the first place. Many millisecond pulsars, including this one, are thought to be spun up by siphoning gas from a companion star, a process so violent it leaves them whirling like cosmic tops. Gravitational waves could reveal the scars of that stellar cannibalism, written in the quiet vibrations of spacetime. For now, PSR J1748 keeps spinning in the dark, its gravitational song still too faint to hear. But when our detectors finally catch that whisper, it won't just be a scientific triumph. It'll be like decoding the diary of a star, written in the language of ripples across the universe. Deep in the cosmic archives of 2020, gravitational wave astronomers stumbled upon a collision that defied the rules, a black hole merger where one participant broke all known limits. The event, catalogued as GW190521, featured a black hole clocking in at 85 times the mass of our Sun, a size that should have been impossible under our current understanding of stellar physics. Here's why this detection sent shockwaves through astrophysics. Stars that massive don't just die quietly. When stars between 65 and 130 solar masses reach the end of their lives, they undergo something called pair instability supernova, a runaway thermonuclear explosion so violent it vaporizes the entire star, leaving nothing behind. No black hole remnant, no neutron star, just stardust scattered across space. Yet GW190521's heavier black hole sat squarely in this forbidden mass gap, mocking our models. Scientists scrambled for explanations. Maybe this was no ordinary star-born black hole. but a second-generation monster, the product of earlier mergers in a dense star cluster, where smaller black holes repeatedly collided and combined like cosmic snowballs. Alternatively, it could have been born from the direct collapse of a primordial gas cloud in the early universe, skipping the star phase entirely, the most tantalizing theory. That we'd glimpsed a relic from the Big Bang itself, a primordial black hole, forged in the universe's first chaotic moments. What made this merger even stranger was its partner, a black hole just 66 solar masses, still hefty, but comfortably outside the forbidden range. Together, they spun into each other 7 billion years ago, merging into a single black hole 142 times the mass of our Sun. That final number matters because it crossed another critical threshold, the elusive intermediate mass range, a category of black holes we've rarely observed, bridging the gap between stellar black holes and the supermassive giants lurking in galactic centers. The implications ripple far beyond textbook revisions. If black holes can form or grow into this mass range, they could be the missing seeds for supermassive black holes, explaining how some grew so large so quickly in the early universe. It also raises spine-tingling questions. How many of these rule breakers are out there? Are we looking at a fluke or an entire hidden population of black holes that shouldn't exist? Every anomalous detection like this forces us to rethink the universe's most violent factories, where gravity doesn't play by the rules we wrote. For now, GW1 90521 remains a glorious enigma, a cosmic rebel that reminds us the universe thrives on exceptions. And with each gravitational wave we catch, we're not just filling gaps in our knowledge, we're finding cracks in the foundations where entirely new physics might be hiding. Einstein's equations assume the cosmos played by orderly rules, but throw a third black hole into the mix and all bets are off. Most gravitational wave detections so far have come from clean, binary collisions, two black holes or neutron stars spiraling toward an inevitable merger. But lurking in the universe's darker corners are chaotic three-body systems, where black holes orbit each other in a gravitational ballet so unstable it defies prediction. These frenzied trios don't just produce gravitational waves, they warp spacetime in ways that could push general relativity to its breaking point. Picture three black holes trapped in a cosmic game of musical chairs. Their orbits aren't neat ellipses, but wild, looping paths where one black hole might suddenly get ejected at incredible speed while the other two merge, or all three might collapse together in a messy, three-way collision. Unlike binary systems where waves follow a steady chirp, three-body events would generate erratic, stuttering signals like a record skipping across spacetime. These waveforms could carry fingerprints of chaos theory itself, revealing how tiny changes in initial conditions, like a black hole's starting position, snowball into wildly different outcomes. Why does this matter? Because three-body systems are relativity's ultimate stress test. Einstein's equations struggle to model their behavior analytically. Even supercomputers can only approximate their evolution through brute force number crunching. If LIGO or future detectors catch one of these events, the wave's structure could reveal whether general relativity holds true under such extreme dynamical chaos, or if we're seeing cracks in the theory's foundation. Some modified gravity models, like those involving extra dimensions or quantum corrections, predict subtle deviations in how these systems radiate waves. A single detection might settle debates that have raged for decades. The odds of spotting one are slim for now. Three black hole systems are rare and short-lived, often forming in dense environments like globular clusters where stars and their remnant black holes pack together millions of times tighter than in our galactic neighborhood. Even then, their chaotic dances typically end within millennia, a blink in cosmic time with one black hole flung away as a runaway rogue while the others merge. But next-generation observatories like the Einstein telescope with 10 times LIGO sensitivity could hear these events from much farther away, dramatically increasing our chances. What would a detection sound like? Instead of the clean sweep of a binary chirp, scientists might hear a gravitational wave, glitch, sudden frequency jumps as orbits reconfigure, or bizarre harmonics as one black hole steals energy from the others. There could even be multiple mergers in quick succession, like cosmic dominoes falling. Each irregularity would be a goldmine of information, exposing the raw unpredictability of gravity when it's allowed to run wild. And the implications stretch beyond astrophysics. Three-body chaos might explain some of the universe's most puzzling orphans, like hypervelocity black holes racing through intergalactic space, or intermediate mass black holes that seem too big to form from stars alone. These gravitational wave detections wouldn't just be scientific curiosities. They'd be keys to unlocking the universe's untidiest, most exhilarating gravitational dramas, where even Einstein might have to hold on tight. At the heart of our Milky Way, hidden behind thick veils of dust and light, lies a gravitational storm unlike anything in our cosmic neighborhood, a swirling maelstrom of black holes and neutron stars locked in endless, violent dances. While we've detected individual mergers across the universe, imagine the cacophony of thousands of these events happening simultaneously in the galactic center, their gravitational waves overlapping into a steady, universe-filling hum. This is the gravitational wave background, a whisper so faint we can't hear it yet, but soon, detectors like LISA and the Einstein telescope might tune into this cosmic static, revealing secrets about the densest, most chaotic place in our galaxy. The math is staggering. Within just a few light years of Sagittarius, a star, the supermassive black hole anchoring our galaxy, astronomers estimate tens of thousands of stellar mass black holes and neutron stars orbit like frenzied moths around a flame. Their gravity tugs them into random pairings, triggering mergers at rates hundreds of times higher than elsewhere in the Milky Way. Each collision sends ripples through space-time, but from this distance, their individual chirps blur into a collective murmur, like hearing a stadium crowd's roar instead of single voices. What makes this hum so valuable? Unlike the sharp, isolated waves we detect today, this background would act as a fossil record of our galaxy's most violent history. The hum's frequency range could reveal the average mass of these hidden black holes, telling us whether they're mostly light remnants of dead stars or heavier, mysterious objects from the early universe. Its loudness or lack thereof might hint at how often they merge, shedding light on the chaotic dynamics near Sagittarius, a star, where tidal forces can fling black holes into wild orbits or trap them in dense, swirling mobs. Future observatories won't just hear this hum, they'll deconstruct it. By analyzing how the signal changes over years, scientists could map the population of invisible black holes near the galactic center, even spotting subtle Doppler shifts as waves are distorted by Sagittarius, a star's gravity. Some theories suggest the hum might carry echoes of hierarchical mergers, black holes formed from earlier collisions, their odd spins and masses betraying their violent ancestry. Others wonder if we'll hear the faint traces of dark matter annihilating near these black holes, a process that could warp space-time in ways gravitational waves might expose. But the grandest prize, this background could be time-traveling evidence. The waves from mergers near the galactic core take 26,000 years to reach us, meaning the hum we detect would be a snapshot of that region during Earth's last ice age, when humans were etching symbols onto cave walls. Each ripple is a delayed broadcast from an era when our ancestors gazed at the same stars, unaware of the invisible storms raging at the galaxy's heart. Until detectors mature, this hum remains a hypothesis, a ghostly chorus just beyond our hearing. But when we finally listen, it won't just be noise. It'll be the universe's way of translating chaos into music, revealing the hidden rhythms of a place where gravity writes the rules and space-time never stops trembling. While black holes and neutron stars steal the spotlight, there's another cosmic duo quietly bending space-time in the background: white dwarfs. These Earth-sized embers of dead stars may not pack the raw power of their more extreme cousins, but their gravitational waltzes tell a story of patience and inevitability. Take the system J0651, white dwarfs separated by just 1/3 the distance between Earth and the Moon, orbiting each other every 12 minutes at speeds approaching 6 million kilometers per hour. Their dance is so tight the entire system could fit inside the Sun, and with every revolution they send out gravitational waves that are slowly, relentlessly dragging them toward a fateful embrace. Here's the twist: unlike the explosive mergers of black holes, white dwarf pairs lose energy at a glacial pace. The waves they emit are whispers compared to the cosmic shouts of heavier objects, but they're persistent. Each ripple carries away a tiny fraction of the system's orbital energy, causing the stars to spiral closer by about 1 millimeter per day, a distance so small it would take over 300 years to shave off a single kilometer. Yet this snail's pace adds up. For J0651, calculations suggest a collision in less than 2 million years, a blink in cosmic terms. What makes these mergers special isn't just their inevitability, but what they leave behind. When two white dwarfs finally merge, their combined mass could ignite a runaway thermonuclear reaction, exploding as a Type Ia supernova, the same kind used as cosmic yardsticks to measure the universe's expansion. But if their total mass stays below a critical threshold, something even stranger happens. They collapse into a single, heavier white dwarf, wrapped in a swirling veil of stolen material. Some theories suggest these mergers might birth rare, zombie stars that defy normal stellar evolution, burning unpredictably for eons. The waves from systems like J0651 offer a sneak peek into this future. Their steady, predictable frequency acts like a metronome for gravitational wave astronomers, providing a pristine laboratory to test Einstein's theories over timescales far longer than human observation. Unlike the chaotic mergers of black holes, white dwarf binaries are clocks ticking in slow motion, their waves carrying the unmistakable signature of spacetime's patience. And when detectors like LISA finally tune into THESE Chinese letter HUM, they won't just hear a single pair, they'll catch the murmurs of thousands of these doomed duos, a chorus of countdowns scattered across the galaxy, each marking time until a silent ember becomes a celestial firework. Some gravitational wave events unfold like slow-motion disasters, black holes circling each other for thousands of orbits before finally merging. But in April 2019, the universe delivered a shock. A pair of black holes that barely had time to say hello before crashing together. Detected by LIGO and Virgo, GW1 90426 lasted just 10 seconds from first detection to final collision, a merger so fast it left scientists scrambling for explanations. These black holes weren't just flirting with catastrophe, they were diving headfirst into it, completing their death spiral in less time than it takes to boil an egg. What made this merger so bizarre? Normally, black holes spend eons, or at least hours, dancing closer as gravitational waves sap their orbital energy. But these two skipped the courtship entirely, suggesting they were practically born on the brink of collision. The leading theory: they met in an ultra-dense stellar environment, like the chaotic core of a globular cluster, where thousands of stars and black holes pack into a space just a few light years wide. In such a cosmic mosh pit, violent encounters are common. One black hole might get hurled toward another by a close gravitational pass, entering orbit already millimeters from disaster. Or perhaps they were the products of earlier mergers, second-generation black holes kicked into reckless paths by the energy of their own violent births. The speed of their merger wasn't the only surprise. The signal's shape suggested at least one of the black holes was spinning furiously, its rotation warping spacetime like a vortex as it plunged toward its partner. Such extreme spins hint at a turbulent life story. Maybe it was sent spinning by previous near misses with other black holes, or spun up by swallowing stars whole. Either way, the collision itself was over in a flash, unleashing energy equivalent to 8 suns converted into pure gravitational waves. This event forced astronomers to rethink how often black holes might merge almost instantly. If GW1 90426 wasn't a fluke, there could be entire populations of black holes in dense clusters locked in these gravitational quick-draw duels. Future detectors like the Einstein telescope could reveal whether these fast mergers are rare outliers or hidden signatures of the universe's most crowded neighborhoods, places where gravity doesn't bother with introductions before rewriting the rules. Gravitational waves haven't just confirmed what we know about black holes, they've exposed glaring gaps in our understanding, one of the most puzzling revelations. The so-called mass gap problem, where detectors keep finding black holes that shouldn't exist based on everything we know about how stars live and die. Take the event GW1 90521, a collision featuring an 85 solar mass black hole, a size that sits squarely in a theoretical no-man's land. According to stellar evolution models, stars in this mass range should annihilate themselves so completely in death that no black hole remnant could possibly form. Yet here they are, defying the rules with every gravitational ripple they send our way. The mystery boils down to a cosmic catch-22. When massive stars, those between 65 and 130 times the mass of our Sun, reach the end of their lives, they don't just collapse quietly. Instead, they undergo pair instability supernova, explosions so violent that the entire star is vaporized, leaving nothing behind. No remnant, no black hole, just a scattering of stardust. So how do we keep finding black holes in this forbidden weight class? One compelling theory suggests these outliers aren't born from single stars at all, but are instead second-generation mergers, black holes that formed when smaller predecessors collided in dense star clusters, snowballing into masses that break the stellar limit. But there's a wilder possibility: primordial black holes, hypothetical relics from the universe's earliest moments. Unlike stellar black holes, these wouldn't be born from dying stars but from ultra-dense regions of spacetime in the chaotic aftermath of the Big Bang. If they exist, they could solve multiple cosmic puzzles at once, not just the mass gap, but also the elusive nature of dark matter. Some theories propose that primordial black holes in this gap range might be the invisible glue holding galaxies together, their gravity shaping the cosmos in ways we're only beginning to sense. The debate is far from settled. Each new gravitational wave detection adds another data point to the puzzle, and some events like GW1 90464, featuring a black hole just shy of the gap's lower edge, hint at a continuum rather than a clean cutoff. Could this mean our stellar models need tweaking, or are we seeing the fingerprints of entirely new physics where black holes form through mechanisms we haven't even imagined yet? What's thrilling is that every anomaly forces us to rethink the universe's rulebook. The mass gap isn't just an academic curiosity, it's a frontier. Whether the answer lies in revised astrophysics, ancient cosmic relics, or something even stranger, one thing's clear: gravitational waves are showing us that the universe's most extreme objects still have secrets to spill. And with each detection, we're not just filling gaps in our knowledge, we're discovering where the map ends and the real adventure begins. Among the most tantalizing possibilities in gravitational wave astronomy is that we might one day catch the echoes of a wormhole, a tunnel through spacetime itself. Unlike black holes, which swallow everything that crosses their event horizons, wormholes could theoretically connect distant parts of the universe or even different universes entirely. And if they exist, their gravitational wave fingerprints would be unlike anything we've detected so far. Imagine two black holes merging, but instead of a clean collision, their signals bounce back like a shout reverberating in a cave. That's the telltale signature physicists predict for a wormhole. Here's why: if black holes were connected by a wormhole, their gravitational waves wouldn't just ripple outward. Some waves would pass through the wormhole's throat, emerge on the other side, and loop back, creating delayed echoes superimposed on the original signal. These wouldn't be random noise, but precise, repeating distortions, fading like a cosmic version of a ringing bell. The math behind this is mind-bending. Wormholes, assuming they're stable, would act like cosmic mirrors for spacetime vibrations. When black holes orbit near a wormhole's mouth, their gravitational waves could split, some escaping normally, others taking a shortcut through the tunnel and reappearing milliseconds or even seconds later. The result, a signal that looks eerily similar to the original merger but subtly shifted, like an audio recording layered with its own delayed playback. Scientists are already scouring LIGO data for these echoes. In 2017, one team claimed to have found tentative evidence in the aftermath of GW1 509414, the first detected black hole merger. Their analysis revealed faint, repeating patterns in the signals, ring down, the fading vibrations after the merger. Skeptics argue these could just be statistical fluctuations, but if confirmed, it would revolutionize our understanding of spacetime's architecture. The echoes wouldn't just prove wormholes exist, they'd reveal their size, shape, and even how long the tunnel might be. The catch, wormholes, if they're out there, are likely unstable without exotic matter, a hypothetical substance with negative energy that could prop open the tunnel against collapse. No such material has ever been observed, but gravitational wave echoes might be our first indirect evidence. And the hunt isn't limited to LIGO. Future observatories like the Einstein telescope, with their vastly improved sensitivity, could catch these whispers with crystal clarity, separating true echoes from cosmic static. What's at stake isn't just a sci-fi fantasy. Wormholes challenge the very foundations of general relativity, offering potential pathways for time travel, faster-than-light shortcuts, or even bridges to other dimensions. Every unexplained blip in gravitational wave data could be a clue, a faint reverberation from a doorway hidden in plain sight, waiting for us to listen closely enough to hear it knock back. Dark matter has always played hide and seek with scientists, invisible, untouchable, yet making up 85% of the universe's mass. But what if gravitational waves could finally force it out of hiding? There's a tantalizing theory that some ripples in spacetime might not come from black holes or neutron stars at all, but from dark matter itself collapsing or annihilating in catastrophic events we've never witnessed. This wouldn't just be a breakthrough, it'd be a cosmic 2-for-1, solving two of astronomy's biggest puzzles with a single signal. Picture a clump of dark matter, an invisible, amorphous blob drifting through space. Unlike ordinary matter, dark matter doesn't emit light or collide with atoms, but it does exert gravity. Now imagine that blob growing denser over time, pulled together by its own gravity until it reaches a tipping point. Some models suggest that under extreme conditions, dark matter particles could annihilate upon contact, converting their mass into pure energy. That sudden release wouldn't just vanish, it would send shockwaves through spacetime itself, generating gravitational waves with a signature unlike anything from stellar collisions. The beauty of this idea lies in its simplicity. If we detected such a wave, its frequency and structure could reveal dark matter's properties, whether it's made of hypothetical particles like actions or WIMP, weakly interacting massive particles, or something even stranger. Unlike traditional dark matter searches, which rely on indirect clues like galaxy rotations or gravitational lensing, gravitational waves would offer a direct audio feed of dark matter's behavior in real time. One particularly wild scenario involves primordial black holes, hypothetical dark matter candidates born in the universe's first seconds. If these ancient black holes exist in certain mass ranges, their mergers could produce gravitational waves that look subtly different from those of star-born black holes. Some researchers are already sifting through LIGO data for these anomalies, hunting for waves that might betray dark matter's fingerprints, but the implications go deeper. If dark matter can collapse or annihilate, it might explain why we haven't found it yet in particle colliders. Its most dramatic interactions could be vanishingly rare, occurring only in environments where gravity overpowers all other forces. A gravitational wave from such an event would be like catching a ghost mid-transformation, a fleeting glimpse of the invisible machinery shaping our cosmos. For now, the hunt is speculative, but the stakes couldn't be higher. Every unexplained ripple in the gravitational wave background could be a clue, a whisper from the dark side of the universe. And if we ever tune into that signal, it won't just rewrite physics textbooks, it'll pull back the curtain on the universe's best-kept secret, revealing the hidden hand that's been shaping galaxies, bending light, and orchestrating the cosmos from the shadows. When a star dies in the most violent way imaginable, not just as a supernova, but as a hypernova, an explosion so fierce it outshines entire galaxies, it doesn't just rip apart a star. It tears at the fabric of spacetime itself. These cosmic detonations are the universe's ultimate power plays, unleashing energies that dwarf even black hole collisions. And unlike light, which takes time to escape the chaos, gravitational waves from a hypernova surge outward the instant the star's core collapses, making them the fastest messengers in the cosmos. Here's how it works when a hypergiant star, dozens of times more massive than our Sun, exhausts its nuclear fuel. Its core doesn't just implode, it detonates like a thermonuclear bomb with the force of 100 ordinary supernovae. The collapse happens in milliseconds, but the shockwave that follows is where things get surreal. As the star's outer layers recoil from the collapsing core, they create a jet of plasma moving at nearly the speed of light. This jet punches through the star's remnants, heating the surrounding gas to billions of degrees and triggering a gamma-ray burst, the most luminous electromagnetic event since the Big Bang. But here's what's mind-blowing. While the gamma-ray burst takes precious seconds or even minutes to fight through the superheated debris, gravitational waves don't wait. The moment the star's core buckles, spacetime reacts instantaneously, sending ripples outward at light speed, untouched by the swirling plasma, unfazed by the magnetic storms. These waves are the universe's breaking news alert, arriving before the light show even begins. It's like feeling the thunder of a distant explosion before the sound reaches you, except in this case, the thunder is the fabric of reality trembling, and the sound is a light beam struggling to escape the wreckage. Why does this matter? Because hypernova are cosmic gold mines for astrophysics. Their gravitational waves carry pristine details about the collapse's exact moment. The shape of the imploding core, the speed of the jet formation, even the star's rotation before death. Traditional telescopes see only the aftermath, like forensic investigators arriving at a crime scene hours later. Gravitational waves, though, they're the eyewitnesses, capturing the star's final microseconds in real time. Imagine the potential. If we detect both the gravitational waves and the gamma-ray burst from the same hypernova, the time delay between them could map the explosion's internal structure. A shorter delay might hint at a cleaner collapse, while a longer gap could suggest a more chaotic environment, with the jet fighting through thick stellar material. Each waveform becomes a Rosetta Stone, translating the hidden physics of these apocalyptic events. Yet for all their ferocity, hypernova gravitational waves remain elusive. Their signals are shorter and messier than the clean chirps of black hole mergers, buried under the noise of a restless universe. But next-generation detectors like the Cosmic Explorer or Einstein telescope could change that. With sensitivity tuned to catch these fleeting tremors, we might soon witness the universe's fastest, most violent deaths, not through the glow of their aftermath, but through the shudders they send racing through spacetime itself, proof that even in destruction, the cosmos leaves nothing to waste. Gamma-ray bursts are the universe's most powerful explosions since the Big Bang, cosmic detonations so fierce they outshine entire galaxies in mere seconds. But hidden within these blinding flashes of light may be something even more extraordinary: gravitational waves carrying secrets about the violent engines powering them. While we've yet to detect these waves directly, their potential discovery could crack open one of astrophysics' greatest mysteries: what actually triggers these apocalyptic blasts. Picture the aftermath of a massive star's collapse, where a newborn black hole or neutron star spins wildly, sucking in surrounding matter at nearly light speed. This cosmic dynamo channels unimaginable energy into twin jets of plasma that drill through the dying star like celestial blowtorches. When those jets break free, they create the gamma-ray burst we observe, but simultaneously, the chaotic wobbling of the central engine sends gravitational waves rippling through spacetime. Unlike the clean chirps of black hole mergers, these waves would be messy, erratic tremors, mirroring the instability of matter being shredded and accelerated to relativistic speeds. What makes these gravitational signals so valuable is their ability to peer where light cannot. Gamma rays show us the aftermath, the jets already in flight, but gravitational waves would capture the central engine's birth pangs in real time. The waveform might reveal whether the burst is powered by a hyper-magnetized neutron star, a magnetar spinning itself apart, or a black hole swallowing matter so fast it chokes and regurgitates energy in focused beams. Some models even suggest these waves could expose kicks during formation, moments when the newborn black hole gets violently shoved off-center by asymmetric explosions, sending it careening through space while still devouring its surroundings. The challenge lies in catching these fleeting signals. Gamma-ray bursts last anywhere from milliseconds to minutes, and their gravitational waves would be equally brief, but potentially detectable if the burst occurs within a few 100 million light-years. Future observatories like the Einstein telescope or Cosmic Explorer, with sensitivities tuned to higher frequencies, might finally spot these whispers beneath the cosmic noise. A single detection could settle decades-old debates about whether most bursts come from collapsing stars, long-duration bursts, or merging neutron stars, short bursts, while revealing how much energy gets channeled into warping spacetime versus lighting up the universe. Perhaps most intriguing is the possibility of orphan gravitational wave signals without any visible burst at all. Some jets may fail to pierce their stellar cocoons, trapping their light but still shaking spacetime. Others might beam their radiation away from Earth while their gravitational waves reach us unimpeded. Finding these hidden events would unveil a shadow population of failed or misaligned bursts, proving that for every gamma-ray flash we see, countless more might be vibrating the cosmos in silence. Every unexplained ripple in gravitational wave data could be a clue, not just to how stars die, but to how black holes and neutron stars are born screaming into existence, twisting spacetime itself in their violent arrival. And when we finally capture that signal, it won't just be a detection. It'll be like placing a stethoscope against the chest of a supernova, listening to the universe's most catastrophic explosions from the inside out. Einstein's theory of general relativity paints gravity as the smooth bending of spacetime, a cosmic trampoline where planets and stars create dips that guide their motion. But zoom in close enough and this elegant picture falls apart. At the quantum scale, where particles flicker in and out of existence, gravity refuses to play by the same rules as other forces. This glaring gap in physics, the quest to reconcile gravity with quantum mechanics, has haunted scientists for a century. And now, gravitational waves might hold the key to cracking it wide open. The secret lies in the highest frequencies of these spacetime ripples, vibrations so rapid they'd make a hummingbird's wings seem slow. Most gravitational waves we detect, like those from black hole mergers, are low-frequency rumbles, cosmic bass notes. But theorists suggest that in the universe's first fleeting instance, conditions were so extreme that spacetime itself may have vibrated at quantum scales, producing ultra-high-frequency gravitational waves. These waves, if they exist, would carry imprints of spacetime's granularity, proof that gravity, like matter, comes in discrete packets or quanta. Why is this the Holy Grail? Because quantum gravity governs the most extreme environments in existence, the centers of black holes where density becomes infinite, and the Big Bang itself where all physics breaks down. Without understanding how gravity operates at these scales, our theories hit a wall. Current detectors like LIGO can't hear these high-pitched whispers. Their frequencies are 1,000,000 billion times higher than what our instruments can catch. But future technologies like space-based quantum sensors or cryogenically cooled mirrors might one day tune into these echoes from the dawn of time. The implications stagger the imagination. High-frequency gravitational waves could reveal whether spacetime is fundamentally pixelated, woven from tiny loops or strings too small to see. Some models predict these waves would exhibit subtle anomalies like unexpected harmonics or frequency cutoffs that betray the presence of quantum foam, a turbulent sea of virtual black holes and wormholes bubbling beneath reality's smooth surface. Others suggest the waves might carry hints of extra dimensions, their vibrations leaking into hidden folds of the cosmos. What makes this hunt so electrifying is that it's not just about filling a gap in equations. It's about probing the universe at energies so extreme they haven't existed since the first trillionth of a second after the Big Bang. Every other force, electromagnetism, the strong and weak nuclear forces, has been quantized. Gravity remains the lone holdout, the rebel that refuses to fit the pattern. Catching its quantum whispers wouldn't just complete physics' greatest puzzle, it would rewrite our understanding of reality itself, revealing whether spacetime is continuous or stitched together from something far stranger. For now, these waves remain theoretical phantoms, their existence debated in papers and chalkboard scribbles. But if we ever detect them, it won't just be a discovery. It'll be like finding the universe's Rosetta Stone, a cipher to decode the deepest language of existence, spoken in vibrations finer than atoms, older than stars, and louder than silence. What if our universe isn't just 3 dimensions of space and 1 of time, but something far stranger, a cosmic layer cake with hidden dimensions curled up so tightly we've never noticed them? String theory, the boldest attempt yet to unify gravity with quantum mechanics, predicts exactly that: extra dimensions, perhaps 6 or 7 of them, folded into microscopic loops at every point in space. And if they exist, gravitational waves might be our best shot at uncovering them. Here's how these hidden realms could leave fingerprints in spacetime's ripples. Normally, gravitational waves weaken as they travel, their energy spreading thin across the expanding fabric of the universe. But in a cosmos with extra dimensions, some of that energy could leak into these unseen layers, subtly altering the wave's amplitude or frequency by the time they reach our detectors. It's like listening to music through a wall. The bass might fade first, hinting at unseen spaces absorbing the sound. For gravitational waves, even a tiny deviation from Einstein's predictions could betray dimensions lurking just beyond our perception. The most tantalizing clue would come from high-frequency waves, the kind generated in the earliest moments of the Big Bang or by exotic objects like cosmic strings. These vibrations, with wavelengths shorter than an atom, might feel the extra dimensions more acutely, resonating in ways that warp their shape. Imagine plucking a guitar string. The note changes if you press your finger halfway down, revealing the string's hidden length. Similarly, high-frequency gravitational waves could probe the compact geometry of these dimensions, their harmonics shifting in ways no 3-dimensional model can explain. Future detectors are being designed to catch these whispers. Projects like the Lunar Gravitational Wave Antenna LIGO aim to place sensors on the Moon, where the lack of atmosphere and seismic noise could reveal ultra-high frequency waves. Others propose using clouds of ultra-cold atoms or even pulsar timing arrays, networks of rapidly spinning neutron stars, as galactic-scale detectors sensitive enough to spot anomalies. A single anomalous wave, one that dims or distorts in ways that defy relativity, might be the smoking gun for dimensions beyond our own, but the implications go far beyond gravitational waves. If extra dimensions exist, they could explain why gravity is so weak compared to other forces. It might be spread thin across these hidden layers. They might even house entire parallel universes, separated from us by less than a millimeter but inaccessible except through these subtle space-time tremors. Every unexplained quirk in gravitational wave data becomes a potential doorway, a crack in reality's facade where the true scale of the cosmos peeks through. For now, these dimensions remain theoretical, their existence debated in equations and thought experiments. But if we ever catch that telltale ripple, one that shouldn't exist in a four-dimensional world, it won't just rewrite physics. It'll tear open the universe's blueprints, revealing a reality far grander and more bizarre than we ever dared dream. When two black holes collide, the universe doesn't just witness a merger, it hears a cosmic bell toll. The moment the event horizons touch, the newborn black hole doesn't settle quietly. Instead, it vibrates violently, shaking space-time like a struck gong in what physicists call the ring-down phase. These aren't random tremors, they're precise oscillations that encode the black hole's deepest secrets in gravitational waves, revealing details no telescope could ever glimpse. Picture a bell freshly struck. The initial clang fades quickly, but the metal continues humming at specific tones called quasi-normal modes. Black holes behave similarly after merging, radiating gravitational waves at characteristic frequencies that decay exponentially as the new singularity settles into equilibrium. The pitch and decay rate of these tones aren't arbitrary. They're dictated by the black hole's final mass and spin, with mathematical precision that would make a Swiss watchmaker weep. A more massive black hole rings at lower frequencies, while rapid rotation splits the signal into multiple harmonics, like a chord played on a celestial piano. What's astonishing is how much information these vibrations carry. By analyzing the ring-down's waveform, scientists can deduce not just the new black hole's mass, but whether it's slightly squashed or elongated, a property called its quadrupole moment. According to Einstein's equations, a black hole's mass, spin, and quadrupole moment are locked in an exact relationship known as the no-hair theorem. Any deviation in the ring-down pattern could mean we're seeing something revolutionary, perhaps evidence of exotic matter clinging to the event horizon, or even cracks in general relativity itself. The most famous ring-down detection came from GW1. 509414, the first gravitational wave ever observed. After the black holes merged, the signal didn't cut off abruptly. It faded over about 30 milliseconds with a distinctive wobble, like a spinning coin settling on a table. This afterglow contained fingerprints of the final black hole's properties, 62 solar masses spinning at 67% the speed of light. Remarkably, these measurements matched predictions made a century earlier using nothing but Einstein's field equations and supercomputers running simulations. But ring-downs aren't just cosmic identification tags, they're time machines. The wave's decay rate reveals how quickly the black hole becomes a perfect, featureless singularity, shedding all hair except mass, spin, and charge. This process is nature's ultimate eraser, destroying information about what fell in a paradox that still puzzles physicists. Some theories suggest quantum effects might leave subtle imprints on the ring-down, clues to what really happens at the event horizon's edge. Future detectors with precision 100 times greater than LIGO could spot these quantum whispers, peering closer to a black hole's true nature than ever before. Perhaps the most mind-bending possibility is that ring-downs might expose black holes that aren't black holes at all. Certain exotic alternatives, like gravastars or wormholes, would produce ring-down signatures with telltale differences, echoes, or irregular decays. In 2021, one team claimed to find such anomalies in existing data, though the results remain controversial. If confirmed, it would mean some objects we've labeled black holes might be stranger entities entirely, their true identities hidden until the universe's most violent events made them sing. Every ring down is a cosmic sonnet written in the language of warped spacetime. And as our detectors grow more sensitive, we're not just hearing the universe's loudest crashes, we're learning to decipher the quiet afternotes, the fading vibrations that may hold answers to gravity's greatest mysteries. Einstein's equations predict that when stars collapse, they can crush down into singularities, infinitely dense points where spacetime itself breaks down. But nature seems to have a rule against letting these cosmic monsters run wild. The cosmic censorship hypothesis proposed by physicist Roger Penrose suggests there's a cosmic bouncer at work. Every singularity must be hidden behind an event horizon, trapped inside a black hole where it can't wreak havoc on the rest of the universe. It's the universe's way of saying, what happens in the singularity stays in the singularity. But what if that's not always true? Gravitational waves might be our best tool to test this rule, and the consequences could shatter our understanding of physics. Imagine a naked singularity, a singularity without an event horizon, exposed to the universe like an open wound in spacetime. Unlike black holes, which keep their secrets locked behind a one-way membrane, naked singularities would let the chaos inside spill outward. Time and space would twist into knots around them, physics would lose all predictability, and the universe would become a lawless frontier. The cosmic censorship hypothesis exists precisely to prevent this nightmare scenario, arguing that nature must always dress singularities behind event horizons. But how do we know for sure? Enter gravitational waves. If a naked singularity ever formed, say, from a lopsided collapse or a near light-speed collision, it wouldn't produce the clean chirp of a black hole merger. Instead, its gravitational waves would carry bizarre, unpredictable distortions, sudden frequency spikes, chaotic oscillations, or even echoes bouncing off the singularity's exposed core. These anomalies would violate the smooth, ordered waveforms predicted by general relativity, offering smoking gun evidence that something far stranger is at play. LIGO and Virgo are already on the hunt for these rule breakers, sifting through their data for waveforms that don't fit Einstein's mold. The stakes couldn't be higher. If cosmic censorship fails, it wouldn't just mean singularities can run free. It would imply that Einstein's equations under extreme conditions allow reality itself to break down. Some theories, like loop quantum gravity, suggest singularities might not even exist, that quantum effects would prevent infinite densities, leaving behind exotic remnants instead. Gravitational waves from a naked singularity could tip the scales, showing us where relativity fails and new physics must take over. For now, every black hole merger we detect is a vote in favor of cosmic censorship, their clean ring-downs suggesting orderly singularities safely hidden away. But the universe loves exceptions, and if we ever catch a gravitational wave that howls instead of chirps, it won't just be a discovery, it'll be a revolution, proving that even space-time has its limits and the cosmos is far wilder than we dared imagine. The most catastrophic collisions in the universe don't whisper, they roar with the force of a space-time tsunami. When two supermassive black holes, each weighing billions of times our sun's mass, finally spiral into each other after a cosmic dance lasting eons, their merger doesn't just send out gravitational waves, it unleashes a shockwave powerful enough to ripple across millions of light years, warping the fabric of reality on scales we can barely fathom. These aren't the fleeting chirps detected by LIGO. They're gravitational tremors so vast their wavelengths could span entire star clusters, vibrating for years or even decades as the black holes complete their final crushing embrace. What makes these mergers so unimaginably powerful? Consider the numbers. A typical stellar black hole collision might radiate energy equivalent to a few suns. A supermassive duo, though, can convert thousands of solar masses into pure gravitational waves in one apocalyptic instant. The frequencies are just as extreme picture waves, oscillating not hundreds of times per second like LIGO detections, but once every month or even year, their undulations so slow they'd make glaciers seem swift. These waves don't just pass through planets, they subtly alter the orbits of stars, stretching and squeezing entire galaxies in their wake. Here's the catch: our current ground-based detectors are deaf to THI's Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter. LIGO arms, though exquisitely sensitive, are too short to catch waves with wavelengths longer than Earth itself. That's where missions like the Laser Interferometer Space Antenna, or LISA, come in. Slated for launch in the 2030s, LISA will consist of 3 spacecraft flying in a perfect triangular formation, trailing Earth in orbit around the Sun with arms millions of miles long. By precisely monitoring the distance between these satellites using lasers, it'll detect the infinitesimal stretching of spacetime caused by passing gravitational waves like a galactic seismograph tuned to the universe's deepest vibrations. The data LISA collects won't just be groundbreaking, it'll rewrite cosmic history. Supermassive black hole mergers are thought to drive galaxy evolution, their gravitational waves carrying clues about how galaxies like our Milky Way grew by cannibalizing their neighbors. Some theories suggest these mergers might even fling stars clear out of their host galaxies, creating hypervelocity stragglers streaking through intergalactic space. And if we're lucky, the waves might reveal even wilder possibilities: chains of mergers where black holes grow hierarchically, stacking like cosmic Russian dolls, or the presence of elusive intermediate mass black holes, the missing link between stellar remnants and supermassive giants. But perhaps the most tantalizing prospect is eavesdropping on the mergers themselves. Unlike stellar black holes, which collide in seconds, supermassive pairs can take years to merge once they're close enough to radiate detectable waves. LISA could track their entire in-spiral like a slow-motion replay, measuring how their orbits decay as they shed energy. The waveform might even expose whether spacetime around them is warped by dark matter halos, or if their event horizons are bumpy from cosmic debris. It's like watching 2 whirlpools in a pond spiral toward each other, except the pond is the universe and the ripples rewrite physics, and the echoes of these tsunamis might linger far longer than the events themselves. Some models suggest the gravitational wave background from countless supermassive mergers across cosmic time could still be washing over us, a fossilized hum quieter than the vibration of a single atom, yet carrying the combined imprint of every galaxy that ever collided. Future pulsar timing arrays, which use the regular flashes of neutron stars as cosmic metronomes, might one day tease out this whisper, revealing how often the universe's titans clashed in the darkness. When LISA finally opens its ears to the cosmos, it won't just detect waves, it'll tune into the bassline of the universe itself, a soundtrack of collisions so vast they make black holes seem like pebbles dropping into a pond. And hidden in THOSE Chinese letter VIBRATIONS could be answers to questions we haven't even thought to ask yet. Most stars go out with a bang, supernova so bright they outshine entire galaxies. But hidden in the cosmic shadows are stellar deaths so quiet they barely leave a trace. These silent supernovae are the universe's greatest disappearing acts, massive stars that collapse straight into black holes without the usual fireworks, their only farewell a ripple in spacetime itself. Here's how it happens. Normally, when a massive star exhausts its nuclear fuel, its core collapses under gravity's crushing weight, triggering a shockwave that rips the outer layers apart in a blinding explosion. But under the right conditions, particularly in stars between 25 and 40 times the Sun's mass, that shockwave can fizzle out, strangled by the sheer density of material falling inward. Instead of rebounding, the core implodes silently, bypassing the explosion phase entirely and forming a black hole in near-total darkness. No brilliant flash. No expanding nebula, just the star winking out of existence, leaving behind a gravitational wave signature as its only epitaph. The challenge in studying these events lies in their invisibility. Traditional astronomy relies on light. Supernovae announce their deaths across millions of light years with bursts of radiation. But a silent collapse emits nothing detectable except gravitational waves, making it the ultimate cosmic ghost. Even neutrinos, the fleeting particles that usually flood from supernova, might be swallowed whole by the newborn black hole before they can escape. Without gravitational wave detectors, we'd have no way to know these stellar vanishing acts were happening at all. Yet these quiet deaths might hold answers to some of astrophysics' most stubborn puzzles. For one, they could explain why we've observed fewer supernovae than models predict. Some stars might be skipping the explosion stage entirely. They might also account for the surprisingly heavy black holes LIGO has detected, as silent collapses could leave behind larger remnants than explosive supernova, which blast away significant mass. And then there's the mystery of supernova asymmetry. Explosive supernova often leave behind neutron stars hurtling through space at incredible speeds, kicked by lopsided detonations. Silent collapses with no explosion to unbalance them might produce black holes that sit nearly still, altering our understanding of how compact objects move through galaxies. The hunt for these events is like searching for footsteps in the dark. Current detectors like LIGO are tuned for the violent clashes of black holes and neutron stars, not the solitary collapse of a single star. But next-generation observatories with improved low-frequency sensitivity might catch the telltale thud of a massive star's core buckling, a waveform very different from the chirps of mergers, more like a sudden, dampened shudder in spacetime. Some theorists even suggest looking for indirect clues, like the abrupt disappearance of a star in pre-collapse telescope surveys, paired with a gravitational wave blip at the same moment. What makes silent supernovae so fascinating isn't just their stealth, but what they reveal about stellar demise's fine line between spectacle and secrecy. For every star that dies in a blaze of glory, others might slip away unnoticed, their stories written not in light but in the quiet distortions of the universe's fabric. And every gravitational wave we catch from these events is like overhearing a whisper in a thunderstorm, a reminder that even in death, stars have more than one way to speak. Deep in the swirling chaos around a black hole's event horizon, an invisible storm might be raging, one made not of matter or light, but of hypothetical particles called actions. These ghostly particles, if they exist, could solve two of physics' greatest mysteries at once: the nature of dark matter and the bizarre gravitational wave signals we've yet to explain. Picture a black hole not as a silent predator, but as a cosmic tuning fork surrounded by a swirling cloud of actions so dense it vibrates spacetime itself, emitting gravitational waves with a signature unlike anything else in the universe. Actions were first dreamed up to solve a puzzle in quantum physics: why the strong nuclear force which glues atomic nuclei together doesn't seem to care about the direction of time. But soon, theorists realized these particles could also be the missing dark matter that outweighs visible matter 5 to 1. Unlike WIMP, their better-known dark matter cousins, actions would be extraordinarily light, billions of times less massive than an electron, and trillions could be streaming through your body right now without a trace. But around black holes, their behavior gets dramatic. Here's where it gets wild. A spinning black hole's immense gravity could trap actions in a dense, invisible cloud stretching thousands of miles across. Like bees swarming around a hive, these particles would orbit in coordinated waves, their quantum properties synchronizing into what's called a superradiant cloud. Over centuries, the black hole's rotation would pump energy into this cloud, making it grow larger and more organized until it starts ringing spacetime like a bell, emitting gravitational waves at precise, mathematically predictable frequencies. The real kicker, these waves wouldn't look like the sharp chirps of colliding black holes. Instead, they'd be a persistent, pure tone, a sine wave humming across the cosmos for years or even centuries, its frequency determined by the action's mass. It's the cosmic equivalent of holding a tuning fork next to a speaker, feedback that builds until the universe itself vibrates in harmony. Detecting this signal would be a 2-for-1 discovery, proving actions exist and revealing their role as dark matter in a single stroke. But why haven't we heard these tones yet? Current detectors like LIGO aren't optimized for such monochromatic waves. They're built for transient crashes, not cosmic lullabies. Future observatories, though, like the Einstein telescope or space-based LISA, could tune into these frequencies with ease. Some theorists are already combing through existing data for hints of these signals, searching for spikes in gravitational wave backgrounds that might betray action clouds around distant black holes. The implications are staggering. If action clouds exist, they'd leave fingerprints beyond gravitational waves. Their gravitational pull could subtly alter the orbits of stars near supermassive black holes, like the one at our galaxy's center. Their decay might even produce faint radio signals, offering another path to detection. And if they are dark matter, their distribution around black holes could explain why some galaxies seem to have fewer stars near their cores than models predict. Action clouds might be pushing them away. What makes this search so electrifying is its sheer audacity. We're not just looking for invisible matter or testing quantum theories, we're listening for the echoes of particles that might be orchestrating the universe's largest structures from the shadows. Every unexplained hum in the gravitational wave background could be a clue, a whisper from a black hole wrapped in a quantum cloak, singing the secrets of the cosmos in a voice we're only now learning to hear. What if gravitational waves could arrive before the cosmic events that created them? It sounds like science fiction, but some theories suggest the universe's most extreme warping of space-time might produce this exact paradox: waves that violate our everyday understanding of cause and effect. Take a supermassive black hole binary where two titans locked in orbit warp spacetime so severely that light, and even gravitational waves, can get trapped in bizarre loops around them. Under these conditions, a wave generated during the final moments of collision might follow a twisted path through spacetime, emerging from the gravitational maelstrom before the merger actually occurs. To an observer, it would look like the ripple preceded the splash, like hearing thunder before seeing lightning strike. This isn't just a quirk of relativity, it's a potential crack in the foundation of causality itself. Einstein's equations allow for such retrograde paths in extreme scenarios where closed time-like curves (CTC) could let information travel backward in local frames of reference. While these wouldn't rewrite history globally, the universe's arrow of time still points forward. They could create pockets where cause and effect appear inverted. Imagine a gravitational wave detector picking up a signal from a black hole merger, only for telescopes to observe the actual collision minutes, hours, or even days later. The implications would force us to question whether before and after are as absolute as we think. Skeptics argue these reversed waves are mathematical artifacts, not physical realities. The extreme conditions needed, like black holes spinning at near-light speeds or orbiting in perfect, resonant harmony, might be vanishingly rare or unstable. Others counter that even if the waves appear to arrive early, they're still bound by cosmic censorship. No real information or energy travels backward, just the illusion of sequence breaking. But a handful of theorists go further, suggesting that if certain quantum gravity models are correct, spacetime's granular structure at microscopic scales might allow for subtle causal effects, where the distinction between past and future blurs at the quantum level. The debate takes an even stranger turn when considering precursor signals in existing data. some analyses of LIGO black hole mergers reveal faint, low-frequency murmurs in the seconds leading up to the main event fluctuations that don't match standard merger models. Could these be echoes of waves arriving early or just noise in the detectors? Future observatories like the Einstein telescope might settle the question with precision sharp enough to spot anomalies in the waveform's very first tremors. What's at stake isn't just a technicality in astrophysics. If time-reversed waves exist even as mathematical curiosities, they'd force us to grapple with the nature of time itself. Is causality truly universal or just a statistical tendency in our corner of the cosmos? Could spacetime's knots and tangles create temporary loops where the future whispers to the past? For now, these questions hover at the edge of theory and observation, a reminder that in the universe's most violent neighborhoods, even the rules we take for granted might bend, twist, or occasionally snap. Imagine the universe as a cosmic sleight of hand, a three-dimensional illusion painted onto a two-dimensional surface, like a hologram emerging from a flat plate. This is the essence of the holographic principle, a radical theory suggesting that all the information in our 3D reality, every galaxy, black hole, and even your thoughts, might actually be encoded on a distant 2D boundary, like the surface of a black hole's event horizon. It sounds like science fiction, but gravitational waves could be the key to proving whether this mind-bending idea is more than just theoretical speculation. The connection lies in the way gravitational waves behave when spacetime is stretched to its limits. According to the holographic principle, the fabric of reality at its most fundamental level isn't smooth and continuous but pixelated like a digital image. These pixels of spacetime would be unimaginably tiny, far smaller than anything we can directly observe, but their existence could leave fingerprints in the gravitational waves produced by violent cosmic events. Specifically, certain quantum fluctuations in the wave's structure might betray this underlying granularity, showing subtle deviations from the predictions of classical general relativity. Picture a black hole merger. As the two singularities spiral toward each other, their immense gravity warps spacetime not just on large scales but down to the Planck level where quantum effects dominate. If the holographic principle is correct, the gravitational waves generated wouldn't just carry information about the black hole's masses and spins, they'd also encode hints about the 2D surface where the universe's true information resides. These hints might appear as anomalous noise in the high-frequency components of the waves, patterns that don't fit Einstein's equations but align with models of a holographic reality. One tantalizing prediction involves how gravitational waves remember their origins. In a holographic universe, information can't be destroyed, it's preserved on the boundary surface, even if it seems lost inside a black hole. This could lead to faint echoes in the waveform long after the main merger signal, subtle repetitions that act like reflections of data bouncing between the 3D event and its 2D shadow. Some researchers have already scoured LIGO data for these echoes, with controversial but intriguing results that continue to spark debate. The implications are staggering. If gravitational waves confirm the holographic principle, it wouldn't just revolutionize physics, it would redefine our place in the cosmos. The three-dimensional world we experience would be a projection, a rendering of deeper, flatter truths. Black holes might not be cosmic dead ends but translators, converting 3D information into 2D code and back again. Even time itself could emerge from this holographic dance, a byproduct of how information is processed on the boundary. For now, the evidence remains elusive, hidden in the quantum noise of spacetime's finest vibrations. But as detectors grow more sensitive, we might one day catch those telltale glitches in the matrix ripples that don't just traverse the universe but reveal its truest, flattest face. And if we do, it won't just be a discovery. It'll be like peeling back reality's curtain and finding the universe's blueprints written in a language of waves waiting to be decoded. What if the gravitational waves rippling through our universe aren't all homegrown? The wildest possibility in cosmology suggests some might be cosmic refugees, echoes from entirely other universes, drifting through the cracks in reality like sound bleeding through a shared wall. This isn't just science fiction. If the multiverse exists, a sprawling foam of bubble universes, each with its own laws of physics, then collisions between these bubbles could theoretically send gravitational shockwaves reverberating across dimensions, leaving faint traces in our detectors. The math behind this idea stretches relativity to its limits. When two universes in the multiverse graze or collide, their membranes or brains might vibrate like drumheads, generating gravitational waves with bizarre properties, frequencies too low or high for our universe's resonance, or waveforms that flicker in and out of detectability as they cross the dimensional boundary. Some models even suggest these waves could arrive sideways, carrying signatures of extra dimensions curled up in ways our instruments aren't designed to catch. Detecting such a wave would be like finding a letter addressed to someone else in your mailbox. Current observatories like LIGO are tuned to frequencies produced by black holes and neutron stars within our universe, events that warp spacetime in predictable ways. A multiverse wave, by contrast, might look like statistical noise, a blip too brief or too strange to fit any known template. It could vanish before verification, dismissed as a glitch. Or it might linger at the edge of sensitivity, whispering in frequencies we've barely begun to explore. The implications of confirmation would rewrite everything. A verified multiverse wave wouldn't just prove other universes exist, it would reveal how they differ from ours. The wave's structure could encode clues about the dimensionality of its home universe, the strength of gravity there, even whether constants like the speed of light are truly constant across realities. If the wave came from a universe where gravity is weaker, for example, its amplitude might decay oddly as it crossed into our stronger gravitational field. Yet the odds are astronomically against us. Even if multiverse waves exist, they'd be attenuated to near nothingness by the journey. The space between universes, if space even applies, might act like an infinite muffler, swallowing their energy. And that's assuming the waves could penetrate at all. Some theories suggest dimensional boundaries are impermeable, sealing each universe in its own spacetime bubble. But here's the thrilling part. We might not need to catch a wave directly to find evidence. The cosmic microwave background, the afterglow of the Big Bang, could bear scars from ancient multiverse collisions like bruises on fruit. Some cosmologists search its patterns for concentric rings or unnatural asymmetries, hints that our infant universe once bumped into a neighbor. Gravitational wave astronomy could cross-check these findings. If a suspicious microwave pattern aligns with an inexplicable ripple in LIGO data, that's two witnesses pointing beyond our cosmic horizon. The search demands new tools. Future detectors like the Big Bang Observer (BBO), a proposed space array, would target frequencies where multiverse waves might hide ultra-low vibrations too stretched for ground-based instruments. Others imagine quantum gravity sensors so sensitive they could pick up space-time tremors from universes where gravity is 1,000 times weaker than here, its waves like feathers brushing against our dimension's fabric. Critics argue this is all speculation squared, a theory chasing a theory. But that's the essence of frontier science, probing the impossible until it flinches. Every unexplained chirp in gravitational wave data, every anomaly in the cosmic background, is a thread tugged from the tapestry of reality. And if one of those threads leads beyond our universe, then the greatest discovery in history won't be finding where we are, but realizing we're not alone in the ultimate sense. That our universe is just one note in a symphony we're only beginning to hear. Right now, gravitational wave astronomy is like listening to the universe through a keyhole. We catch only the loudest, most violent crashes, but in the coming decades that keyhole is about to swing wide open. Next-generation detectors like the Einstein telescope and the Laser Interferometer Space Antenna, or LISA, won't just expand our cosmic hearing, they'll transform it into an all-encompassing symphony, revealing a universe alive with vibrations we've never dared to imagine. The Einstein telescope, planned for underground construction in Europe, will be a game-changer. With sensitivity 10 times greater than LIGO, it won't just detect more black hole mergers, it'll hear them from the edge of the observable universe, catching events so ancient they occurred before Earth even formed. Its triangular design, buried deep to escape seismic noise, could pick up thousands of signals annually, turning today's rare detections into routine cosmic weather reports. Picture this: instead of celebrating one black hole collision every few months, scientists might catalog dozens in a single day, tracing their masses, spins, and locations with pinpoint accuracy. The telescope's low-frequency range will also tune into longer, slower waves like the death spirals of neutron stars hours or even days before they collide, giving us an unprecedented heads-up to point telescopes at the coming fireworks. Then there's LISA, the revolutionary space-based detector set to launch in the 2030s. While ground-based observatories struggle with Earth's noise, LISA-3 spacecraft will float in perfect formation, 2.5 million kilometers apart, connected by lasers precise enough to detect a virus-sized shift in distance. This gargantuan scale lets LISA hunt gravitational waves with wavelengths far longer than any Earth instrument could catch. Waves from supermassive black hole mergers, the kind that shake entire galaxies. THESE, Chinese letter RIPPLES, carry energy equivalent to millions of supernova, yet they're so stretched out, their peaks and troughs can take years to pass by. LISA won't just hear these events, it'll track them in real time, sometimes for decades, as black holes inch closer in a slow-motion dance toward oblivion. But the real magic happens when these detectors collaborate. Imagine the Einstein telescope spotting a neutron star merger in distant space, then LISA later detecting the same star's early in-spiral phases backward in time from our perspective, as their low-frequency waves finally reach us after a billion-year journey. This two-front approach will let us stitch together cosmic timelines like never before, reconstructing the life stories of black holes and neutron stars from birth to collision. And the discoveries won't stop there. With this deluge of data, we might finally crack open some of the universe's hardest puzzles. Are there hidden dimensions crumpled at microscopic scales? Do wormholes exist even fleetingly? Is dark matter whispering through these waves in ways we've yet to decipher? Every unexplained fluctuation in the data could be the first hint of answers, or the start of even deeper questions. What's coming isn't just an upgrade, it's a revolution in how we experience the cosmos. Soon, we won't just be occasional eavesdroppers on spacetime's grandest events, we'll be immersed in them, swimming in a sea of gravitational vibrations that tell the universe's story in a language we're only beginning to understand. The age of silent astronomy is ending, and the universe is about to speak to us in a voice louder and clearer than we ever dreamed possible. From the faint whispers of colliding black holes to the universe shaking tsunamis of supermassive mergers, gravitational waves have ripped open a new chapter in our cosmic story. These 30 mind-bending revelations prove spacetime isn't just the stage for the universe, it's an active participant trembling with secrets. Remember the forbidden black holes lurking in the mass gap defying stellar physics, the pulsar spinning faster than a kitchen blender, flinging gravitational ripples with every rotation. Or the haunting possibility of wormholes echoing through LIGO data like cosmic fingerprints. Each discovery peels back another layer, revealing a cosmos far stranger than we dreamed. But what's truly revolutionary isn't just what we've found, it's how we found it. For centuries, astronomy relied on light, shackled by dust and distance. Now, gravitational waves cut through the noise, delivering unfiltered dispatches from the universe's most violent neighborhoods. They've exposed dark matter's hiding spots, tested Einstein's math in extreme gravity, and even hinted at realities beyond our own. And this is just the beginning. With next-gen detectors like LISA and the Einstein telescope coming online, we're on the brink of hearing the full symphony, from the birth cries of the Big Bang to the murmurs of parallel universes. So stay curious. The next ripple could be anything: a supernova's silent collapse, a neutron star's quantum heartbeat, or something entirely unpredicted. The universe has spent 13 billion years writing its gravitational wave diary, and we've only just learned to read. Drop your wildest predictions in the comments. What'll be the next cosmic headline? A dark matter collision, a time-reversed echo, or a signal so bizarre it rewrites physics forever? One thing's certain: where spacetime trembles, revelations follow. Keep listening. The cosmos is just getting